Good afternoon, everyone, and welcome back to Thermo Shorts. So we've been looking at the first law, and one of the most important things we'll need to be able to do to use the first law is to fix states and find things like specific internal energy. Now, in the last couple classes, we've been talking about linear interpolation. And sometimes we get into this sort of situation where we need to do double interpolation. In this example here, we're interpolating with temperature and with pressure. Now, this can happen virtually anywhere on a TV diagram because it can happen in any phase. But because our data is most sparse for subcooled or compressed liquids, it's most likely, I think, to happen here when we're looking up water in that phase. So in this class, we're going to ask the question, do we have to do double interpolation for liquid water? Now, it turns out that there's a shortcut that we can take, but it involves making an assumption. Now, this is one of the things that we always need to understand as engineers is what are the assumptions that we're making to get to particular equations. So, if we have an incompressible liquid or we have a solid, we can often make the assumption that specific heat is constant. Remember, specific heat, it tells us something about how much energy we have to put in to increase the mass of some substance by 1 degree Celsius. So here we have two different kinds of specific heat. So CV, which is specific heat at constant volume, and it's defined as the partial derivative of specific internal energy with temperature. And we have CP, which is specific heat at constant pressure, which is the partial derivative of enthalpy with temperature. We also have this specific heat ratio, K, which is CP divided by CV. Now, if we make the assumption that CP and or CV are constant, we can use the method of separation of variables and show that the change in specific internal energy is CV times delta T, and the change in specific enthalpy is CP times delta T. Now, this equation can be useful, but we can only use it when we're making this assumption, and we can really only make this assumption for incompressible liquids and solids. Although we'll see if we can expand that a little bit in future lectures. If we have some subcooled liquid, let's call it state 6, which is the same point that we talked about in the last lecture. So what I could do in this case is look at the pressure that we were at for this case, which was 80 bar, find the saturated liquid specific internal energy, and then use constant specific heat to move down so that delta U is equal to CV times delta T, and I can get an estimate for U6. So here, the specific internal energy that I was estimating from this constant specific heat is 205 kilojoules per kilogram. Now, when we looked this up last class, we found out it was just about 175 kilojoules per kilogram. So my error when using this approximation is about 15%. Now, is there something I can do to get a better approximation than this 15%? Maybe I can find some other way of approximating the specific internal energy. And it turns out that if I'm talking about a subcooled liquid, it's a reasonable estimate to say that the specific internal energy for a subcooled liquid at a given temperature and pressure is approximately equal to the specific internal energy of that same liquid. So if we're talking about water, we're still talking about water at that same temperature. So here we're just looking for UF at the temperature that we're talking about. And here you can see that it doesn't matter what pressure we're at if we're talking about the specific internal energy of a liquid at the same temperature, 100 degrees in this case, we get very little change in the specific internal energy. So here, if I'm talking about U for 100 degrees, if my pressure is 1 bar or 300 bar, right? So this is a huge range in pressure. My specific internal energy only changes by about 2%. So this is a pretty reasonable way to estimate specific internal energy if we're talking about a subcooled liquid. So here again, I can check this versus what we did last class. So here, if my state 6 is at this temperature, I can find UF at that temperature, and it's 174.9 kilojoules per kilogram. And in this case, U is essentially identical to the number that I looked up when I was doing double interpolation, which took me a fair bit of time. And even if I was looking at H here, my uncertainty is not too bad at minus 4%. After this, we did an example in this class. So here, this was an isolated system with multiple types of materials in it. I'm not going to read the example to you, but if you'd like to pause it, you can read it yourself. And I'll go over how we solved this problem. So what we're asked to do, we have some water and some copper that are at some initial temperatures. And we're saying that the system is isolated from the surroundings, and we want to know what the final temperature is when everything is at equilibrium. So in this case, the left-hand side of my equation looks a little bit different because I have two different types of material in my system. I'm still assuming negligible kinetic and potential energy changes, so delta E becomes delta U, and I'm still trying to find Q minus W. In this case, we've insulated our system, so there is no heat transfer, but there is some work coming in, and that's the electrical energy that comes in from the resistor. You could model that as being heat if you like. It's just that the sign of that energy term will change if you call that heat. Here, we're changing our delta big U terms to the mass of the material we're looking at, multiplied by CV, multiplied by delta T, right? Because the change in the specific internal energy is CV times delta T. So the change in the internal energy is that multiplied by the mass. Here, I look up CV for copper and for water. Notice that it takes a lot more energy to change 1 kilogram of water by 1 degree than it does for copper. This is why maybe your parents or your grandparents told you that a watched pot never boils, because it takes a long time to heat that water that comes out of your tap at 4 degrees up to 100 degrees before it starts boiling. Again, I modeled the energy coming into the system as work. So here I've put this in. Remember, work in is negative. If I modeled this term as heat, then heat in would be positive. So if this was Q and I canceled out W, Q would be plus 100 kilojoules. And if I put plus 100 kilojoules in here, that's the same as having minus negative 100 kilojoules. So my equation doesn't change if I call this work or if I call this heat. And in this case, my T2 is going to be equal to the same thing for both copper and water. So it's not two unknowns because T2 for copper and T2 for water are the same. I can do a little bit of math here, and I see that my final temperature is 49.3 degrees. So that's an overview of Lecture 9. I'll see you again next time on Thermo Shorts.